So, welcome to the lecture on 2 degree of freedom systems. So, we will consider now the damped damped free vibration of 2 degree of freedom systems. So, we have this system. So, we have such a system that is 2 degree of freedom. So, this is the mass M1, M2, this is K1, K2, K3, C1, C2, C3. So, if we want, and this is the x1 and x2, the 2 degree of freedoms. Now, to study these systems, what we have to do? We have to first write the equations of motion. So, we make the free body diagram, and here one more force is added in compared to the previous analysis, that is the force due to the damping element. So, damping elements C1, C2, C3, they will add certain forces in the equations, and so we write the equations, and that we can write. So, if this is M1, we have the spring force here, damping force here, okay. And then similarly here we have these forces K2 x2 minus x1, C2 x2 dot minus x1 dot, and here K1 x1 and C1 x1 dot. Similarly, this mass will have same forces in the opposite directions, and here these forces K3 x2 and C3 x2 dot. So, and we take this like this. So, these are the forces on the free body diagram, and when we apply the sigma F equal to mx double dot for both the cases, we can write the equations of motion. So, here for example m1 x1 double dot equal to minus k1 x1 minus c1 x1 dot, then plus k2 x2 minus x1 and plus c2 x2 dot minus x1 dot. Similarly, for mass m2, so m2 x2 double dot equal to, so all the forces are opposite to, so they will be minus k2 x2 minus x1 minus c2 x2 dot minus x1 dot minus k3 x2 minus c3 x2 dot. Okay, so this is the equation of motion, and to solve these equations of motion we will assume some solution, like we will assume x1 equal to a1 e power st and x2 equal to a2 e power st. So, when we put here where a1 and a2 they are the amplitude, and so their ratio will govern the or define the mode shape, and S is, and a1 and a2 they are constant, S is also a constant, and when we put in these equations we will find S, and we solve for the S that is the root of that equation, characteristic equation, and from there we will find the final solutions with the help of the initial conditions. So, rather than solving on this system, we take some simple damped system to demonstrate. So let's we have a simple system. So we have this system. So here is this mass, here is a damper, and then there is the second mass, and this is the rigid. So there is no friction between the mass and the surface, and this is K, this is, and here is again one spring. So this is also K, and this is C, this is M, this is M, and so here is it is x1 and this is x2. So this is the system, and now we have to write the equations of motion for this system, this simple system. So this is the first free body diagram of this mass M, first mass. So we will have here this force K x1, well if we pull here it will be K x1 and then this is the damper, and if we assume x2 is greater than x1, so this damper force will pull it C x2 dot minus x1 dot, and this is x1. Now here the second mass will have the same force here C x2 dot minus x1 dot, but opposite direction, and this is spring, because when it will compress it will apply a force K times x2, and here it is x2. So we can write this equation of motion for this system. So here m x1 double dot equal to minus K x1 and plus C x2 dot minus x1 dot. So here m x1 double dot plus C x1 dot plus K x1 equal to C x2 dot. So this is equation 1. Now for the second mass we will have this, so we have to write the equation of motion m x2 double dot equal to, so minus K x2 minus C x2 dot minus x1 dot. So minus K x2 and minus, so because this is in this direction and they are opposite forces, so they will have minus sign. So here m x2 double dot plus C x2 dot plus K x2 equal to C times x1 dot. So this is equation number 2. Now as I said that we have to assume the motion x1 equal to a1 e power st and x2 equal to a2 e power st. So here why we are taking such a form, because s is a complex, it could be complex number, and due to the introduction of damping the motion, the roots could be complex. So that's why we take this kind of solution. And so now we put this here. So, what is x1 dot is s into a1 e power st and equal to s x1, and here x2 dot equal to s a2 e power st. So, that is equal to s x2 Similarly, x1 double dot equal to s square a1 e power st. So, that is s square x1, and x2 double dot equal to s square a2 e power st. So, that is s square x2. So, now we put these values in equation 1 and 2. So, what do we get? So, m x1 double dot. So, x1 double dot is s square and x1 ms square into x1 plus cs x1 plus kx1 equal to cs x2. Now, ms square plus cs plus k x1, and x1 is equal to a1 e power st, a1 e power st, and equal to cs, and x2 is a2 e power st, a2 e power st. So, of course, we can have, because e power st, if we do like ms square plus cs plus k a1 minus cs a2 e power st equal to 0. Of course, e power st is exponential, it can't be 0. So, we have to write ms square plus cs plus k a1 minus cs a2 equal to 0. And so, we can write here a1 by a2 equal to cs by ms square plus cs plus k, and this is equation number 3. So, here we have obtained the amplitude ratio as a function of s. Now, we put these values in equation number 2. So, we get m. So, x2 double dot is s square x2 plus c. So, x2 dot is s x2 plus k x2 equal to c. x1 dot is s x1. So, here ms square plus cs plus k and x2 equal to cs x1. So, here ms square plus cs plus k. Now, x2 is a2 e power st. So, a2 e power st equal to cs x1 is a1 e power st. So, again here ms square plus cs plus k a2 minus cs a1 e power st equal to 0. because e power st can't be 0, we have to write ms square plus cs plus k a2 minus cs a1 equal to 0, and so we can get a1 by a2 equal to ms square plus cs plus k by cs. Okay, so we get this amplitude ratio a1 by a2. Now what we can do, we can equate these two equations 3 and 4 because both are the ratios of a1 by a2, and so therefore we find, we do like cs by ms square plus cs plus k equal to ms square plus cs plus k upon cs. Now we cross multiply, and so we get ms square plus cs plus k square, because these are the same terms, so they will be square equal to cs square. So we can write ms square plus cs plus k square minus cs square equal to 0. Now we can because a square plus b square equal to a plus b into a minus b, so we can use this formula. So ms square plus cs plus k plus cs, and second factor is ms square plus cs plus k minus cs, and this is equal to 0. Okay. So what we get, ms square plus 2cs plus k, and here cs will be cancelled out, so we will have ms square plus k equal to 0. So it means that ms square plus k equal to 0 and ms square plus 2cs plus k equal to 0. So now from these two equations we can get the values of s. So when ms square plus k equal to 0, so s equal to plus minus s square equal to minus k by m, and that is minus complex number j square k by m. So it is j square because minus is equal to j square. So s equal to j root k by m plus minus. And root k by m is, if we say that omega n equal to root k by m, so we can write S12 equal to plus minus j omega n. Now what about this equation? So if we write ms square plus 2cs plus k equal to 0, so we have s equal to minus b, so minus b is minus 2c plus minus under root b square, so b square is 2c whole square, so it is 4c square minus 2ac, so 2 into a is m and c. C is k by 2a, so 2 into a is m, and so we will have this is third and fourth root of s, because we got here two roots. Of course, this is negative minus j root k by m, and this is plus j root k by m, and here 3 by 4. So this we can write minus c by m plus minus under root. So we take m inside, so we will get c by m whole square minus, so here 2 mk by 4 m square, so 2 k m by 4 m square. So here it is 2 and m is cancel out. Minus 4ac, so it is b square minus 4ac, so it is 4 into a into c, so it is 4, here it is 4, so 4 cancel out, we will get k by m. So minus c by m plus minus under root c by m whole square minus k by m. Now c by m equal to 2 zeta omega n. So we have S34 equal to minus 2 zeta omega n plus minus under root 2 zeta omega n square minus, and k by m is omega n square. So we will get minus 2 zeta plus minus under root 2 zeta whole square minus 1 and omega n. Now we assume that this part is such that 1 minus 2 zeta whole square so 2 zeta is, it is less than 1, so it means zeta is less than half, so damping factor is less than half. So we are taking basically the under damp system. So here we will have minus 2 zeta plus minus, so we take it minus outside, so it is j root minus is j under root 1 minus 2 zeta whole square, and this is omega n. Okay, so here we have obtained the roots. Now what will be the solution of this? So here we see that we have the natural frequencies here. So they are, because they are the complex roots, they are in pair, and so we will have a solution like x1 equal to a11 sine omega n1 t plus phi 1, because this root will give us a solution like this, harmonic one, and the other one, due to the second frequency, we will get the solution like a12 exponential minus 2 zeta omega n t into sine root 1 minus 2 zeta or square. So, it is 4 zeta square into omega n t plus phi 2. Okay. So, this you can understand from the because this is complex root. So, we will have some exponential free decay vibration as we discussed the response of the damped response of the single degree of freedom system. So, this is similar, but only here the damping is not zeta, but it is 2 zeta. So, it is 1 minus 2 zeta square is 4 zeta square, and here again minus here it is 2 zeta. Similarly, x 2 will be a 2 1 sine omega n 1 t plus phi 3 plus a 2 2 exponential. So, here it is omega n 1 minus 2 zeta omega this is omega n 2 omega n 2. So, omega n 2 t into sine root 1 minus 4 zeta square into omega n 2 t plus phi 4. So, here we can see these are the response free vibration response of the system, and the values of A1 these constants, that is A11 phi 1, A12 phi 2 or A21 phi 3, A22 phi 4, they will all depend on the initial conditions. Now, if the system is given an initial condition equal disturbance, so if initially we displace both the system with equal amplitude like 5 mm both, then the system will vibrate purely with the first natural frequency, because of course from here we get the mode shape corresponding to the first natural frequency and mode shape corresponding to second frequency. So, when give the equal initial disturbance to both the masses, the system will vibrate with the first natural frequency, and so only the first term, that is sin omega n 1 t plus phi 1 will be there for both the equations. However, if we are giving completely opposite initial conditions, then the system will vibrate with the damped free vibration. So, the second part will be there, because if we put here this S12, we will get A1 by A2 equal to plus 1, and when we put these values we will get A1 by A2 equal to minus 1. So, the system will be in case of omega n2, it will be vibrating as a damped free vibration. Okay, so that is how we can study a damped vibration of 2 degree of freedom system. So, in case of first natural frequency, damper is ineffective. So, there is no role of damper, because both the system they are vibrating as pure sine wave. Okay. When we are, but in other case damper is effective with a damping factor of 2 zeta. Okay. So, I thank you for this lecture and see you in the next lecture.